Kubernetes secrets keep passwords and tokens out of pod specs and images, but they are not magic. You still need access control, careful consumption, and encryption at rest. Secrets are similar to ConfigMaps in shape, but their purpose is different. ConfigMaps are for non-confidential settings. Secrets are intended for passwords, tokens, keys, and credentials. By default, Kubernetes secrets are stored unencrypted in the API server's underlying data store etcd. Base 64 in YAML is not encryption. The data field stores base 64 encoded strings. That makes arbitrary bytes fit into YAML and JSON, but anyone who can read the secret can decode the value. A simple secret manifest looks like an object with metadata and data. If no type is specified, the default type is opaque, meaning arbitrary user-defined data. For labs and quick tasks, kubectl create secret generic is faster. It accepts literals or files and creates an opaque secret without you manually base 64 encoding each value. When creating secrets from literals, remember the shell sees characters like $, \, *, equals, and exclamation point. Single quotes usually avoid accidental expansion. In manifests, stringData lets you write clear text values and let the API server merge them into data. If the same key exists in both fields, stringData takes precedence. Note that stringData does not work well with server-side apply. For production GitOps workflows, be deliberate about how secret manifests are managed. Secret type is more than decoration. Opaque is arbitrary data, but built-in types like Docker config JSON, basic auth, SSH auth, and TLS establish expected keys and sometimes validation. A Docker registry secret is used by kubelet to pull private images for a pod. The secret is referenced at the pod level through image pull secrets. The kubernetes.io/TLS type is for a certificate and private key pair. Kubernetes checks that the required TLS.crt and TLS.key keys exist, but it does not prove the contents are valid for your application. ServiceAccount token. Secrets are a legacy long-lived credential mechanism, and modern Kubernetes prefer short-lived automatically rotating tokens from the token request API or projected ServiceAccount token volumes. The most common secure pattern is mounting secret data as files. Each key in the secret data map becomes a file name, and the file content is the decoded secret value. The pod declares a volume with secret name, and the container mounts it read-only. Only containers with that volume mount can read those files. To verify a volume mount, exec into the pod or use an application log. Listing the mount path should show one file per projected key. Use items when the application expects a specific file path. Only listed keys are projected, and if a listed key is missing, the volume is not created. Secret volume files default to 0644 permissions. You can set default mode, for example 0400 in YAML, to make projected files readable only by the owner. A secret key can start with a dot. When mounted, that key becomes a dot file, so ls-l hides it and ls-la reveals it. Secrets can also become environment variables. Use value from secretKeyRef when one container needs one named value from one secret. With envFrom secretRef, every valid key in the secret becomes an environment variable. This is concise but less explicit than selecting each key. If a secret is consumed as an environment variable, updates to the secret are not seen by the running container. Restart the pod or roll the workload. For secret volumes, kubelet tracks updates and eventually updates projected files. The delay depends on watch, cache TTL, or sync loop strategy. Just like ConfigMaps, secret volumes mounted with subPath do not receive automated secret updates. That mount mode changes the update story. By default, all non-optional secrets must be available before any of a pod's containers start. If optional is true and a secret is missing, Kubernetes ignores it. If a pod references a specific key in a non-optional secret and that key does not exist, startup fails. This is often a typo, not an application bug. The security warning is subtle. Anyone authorized to create pods in a namespace can use that permission to consume secrets in that namespace. Treat pod creation as secret access. RBAC matters. Granting list or watch on secrets lets a subject read all secret data in that namespace, give workloads and humans the minimum access they need. In a multi-container pod, not every container needs every secret. Mount the signing key into the signer container, not the front-end container that handles complex user input. For mounted secrets, kubelet stores a local copy in tempfs, so the data is not written to durable node storage. When the dependent pod is deleted, kubelet deletes its local copy. The docs warn that privileged containers on a node can access all secrets used on that node. Pod security and node isolation matter for secret safety. Static pods are managed directly by kubelet from files on the node. The docs state that you cannot use secrets or ConfigMaps with static pods. Immutable secrets protect against accidental data changes and can reduce API server load at scale. Once immutable, you cannot revert the flag or mutate data. Delete and recreate instead. Encryption at rest in this context protects resource data stored through the Kubernetes API, such as secret objects in etcd. It does not encrypt arbitrary file systems mounted into containers. The API server uses the encryption provider config flag. If it is absent, or if identity is the first provider for secrets, at-rest encryption is not providing confidentiality. An encryption configuration lists resources like secrets, then ordered providers. The first provider encrypts new writes. All listed providers are tried during read so old data can still be decrypted. The identity provider is important but dangerous to misunderstand. It does not encrypt stored data. It is sometimes kept as a fallback during migration, then removed after all relevant data is encrypted. For stronger key handling, the KMS provider uses envelope encryption. Kubernetes encrypts resources with data keys, and a managed service protects those data keys with a key encryption key outside Kubernetes. Locally managed encryption keys improve over plaintext etcd, but the key file lives on control plane hosts. If an attacker compromises the host, they may read the configuration and decrypt data. On kube-ADM-style clusters, the docs show mounting the encryption config into the kube-apiserver static pod and adding the encryption provider config flag. Every control plane host needs the same compatible config. After enabling encryption, newly written secrets should be encrypted in etcd. The docs show checking for a prefix like K8s:ENC:AES:CBC:V1 in the raw stored bytes. Turning on encryption affects new writes. Existing secrets may still be stored as plaintext until they are rewritten. The docs use kubectl get secrets all namespaces piped into kubectl replace. To prevent plaintext retrieval, remove the identity fallback only after confirming all relevant resources are encrypted. Otherwise, the API server may fail to read old plaintext objects. Key rotation is a sequence, especially in highly available control planes. Add the new key as a readable key, restart API servers, promote it for new writes, rewrite secrets, then remove the old key after backup. When a secret setup fails, debug from object to workload. Inspect the secret metadata, check pod events, verify file paths or env names, then check RBAC and encryption configuration if the issue is access or storage. For the exam, keep the workflow crisp, create the secret, consume it as env or volume, verify from inside the pod, and remember that base 64 is not encryption and env changes require restart. The final model is disciplined, not mystical. Put sensitive values in secrets, scope who and what can read them, prefer file mounts when appropriate, and enable encryption at rest for etcd.